Good morning, everybody. So today's going to be a rather quick lesson. I'm going to do just a couple examples from the book. Hopefully this is tying together, and today it's more about recognizing functions and their patterns of change, more closely looking at quadratic functions here and how to recognize a quadratic relationship from its table. And here's a couple of things. I got a linear function right here, and I got a quadratic function right here. So we know this pretty good and well, and we always notice that it's linear when the difference is constant. And we call this the first difference because I can see it's constantly increasing by 3 every time x increases by 1. So this would be considered our slope right here, and we know our y-intercept, which the nice thing about what's synonymous with both linear and quadratic, the y-intercept is always the same for both functions. Whatever x is, that corresponding y value, that's the y-intercept. Whatever x, when x is 0, what's the corresponding y value? That is your y-intercept. Same thing as here. We never write plus or minus 0, just leave it as blank. Now, notice how here on this most basic quadratic function, y equals x squared, I'm looking at my first difference, all right? It's going up by 1, then by 3, then by 5, then by 7. Now, there is some consistency there because the difference, as I've been saying in the past, the difference of the difference is always the same, or as the book is calling it, the second difference, or my language, the difference of the difference. So I can see that this is constantly increasing by 2 every single time, therefore we know it's quadratic. I'm going to do a couple more examples for you, and you'll see how this is true for every single quadratic, because this is what you're doing today. You're going to try to identify that because this is going to help you build quadratic functions from tables eventually, okay? So now if I got one like this, okay, y equals x squared plus 6, you'll notice some similarities between how they increase. I got 0, 1, 2, 3, and 4. Well, when this is 0, this is 6. When this is 1, this is 7. When this is 2, this is 10. When this is 3, it's 9 plus 16, that's 15. I'm sorry, 9 plus 6 is 15. 4 squared is 16 plus 6 is 22. Goes up by 1, goes up by 3, goes up by 5, goes up by 7. That's my first difference. Okay, sorry for the poor handwriting. But then I'm seeing here that this proves to be quadratic because it's constantly going up by 2 in the second difference, or the difference of the difference. Another equation that we can just do, and this will prove that this will always be true. I got 2x squared, let's just say minus 2, okay? So I got 0, 1, 2, 3, and 4. When x is 0, y is negative 2, hence the y-intercept, okay? When x is 1, y is 0, because 1 squared is 1 times 2 is 2, 2 minus 2 is 0. 2 squared is 4, times 2 is 8, minus 2 is 6. 3 squared is 9, times 2 is 18, minus 2 is 16. 4 squared is 16, times 2 is 32, minus 2 is 30. Goes up by 2, goes up by 4, goes up by 10, goes up by 14. And, oops, sorry. This goes up by, sorry about that. This goes up by 6, weirdo. As I see here, my difference is constantly increasing by 4. So now I know that this is quadratic. It's so pretty. Look at Harris door. That's how we know it's quadratic, okay? You're going to be asked to do only part A to recognize some similarities, and by tomorrow and or Friday to see how we do at today's conversation during class, we will start building quadratic functions like the equations from Raw. But the whole point of this is just recognizing what's going on here. See how this is increasing by 2? Coefficient here is 1. This increases by 4. This coefficient is now 2. The last one also increased by 2. The coefficient was 1 of x squared from the previous example. You're going to start to see some similarities, okay? I will be back in a couple seconds with some more examples.